And we're on the air. Here we go. All right, we're in section 2.4, composition of functions. All right, kindly consider the following. Two functions. Okay? What's the composition of function means? That means taking the output of one function, right? You can input into a function, let's say, an x value, and get out a y value, right? But say you take that y value and you plug that into another function. That's called composition of functions, putting one function inside of another. All right? Why is that useful? Why is that convenient? Let's play with this, okay? So kindly consider the following. Let's say C represents the cost in dollars of painting your house, okay? And it's 30.5 N, where N is the number of gallons of paint you need. All right, so N is the number of gallons of paint, and C is the cost in dollars to paint your house, okay? But let's say N, in turn, is the square footage that you're painting, the area, the surface area of your walls, right, divided by 250 square feet per gallon of paint. All right, so the idea is this. If I have to, say I'm going to paint 500 square feet of wall, what's 500 divided by 250? 2, right? So that means I need 2 gallons of paint. That's what this is saying, okay? So N is the number of gallons, or if you want, you ever paint the house? No? Ever paint a wall? The cans, are they gallon cans or are they bigger? Each can is like about a gallon, right? Isn't it? Some they could be bigger, but the standard can is a gallon, right? So N is the number of cans, I guess, really, okay? So N is the number of cans of paint because a can of paint is, say, a gallon, right? But what if then you want to know how much it's going to cost you? So you plug in 500 square feet here. You divide by the 250 square feet. You get 2 cans. You plug into 2 cans, and how much does it cost? Plug in 2 cans. It's going to be 61 bucks, right? That's what composition means. So what if I want to find out what C of, let me be a little more precise. Let's say that C is f of n, a function in n. And n is g of a function of a. What is f of g of a going to represent? That's the question. That's my question. All right, so you're plugging in the number of square feet you're going to have to paint, say the whole house, 10,000 square feet or something, right? You plug that into G, which is this guy, n equals a over 250. You calculate that answer, you get a number, but then you're plugging that into f, which is this function, how much it costs for that many cans of paint. And that's the composition. So can you figure out C as a function of n? I have C as a function of n, right? I have C as a function of n. I want C as a function of a. What is it? How do you figure this? I could do it very easily with numbers, right? Like I did. If I plug in, let's say I plug in 1,000 square feet, divided by 250 square feet, I get 4. Then I plug in 4 times 60 times 30.5, I'll get 120. It's 61 doubled, 122, right? But what if I don't want to do all of that? What if I just want to do this in one swell swoop? What do I do? I'm going to plug into, hang on. It doesn't have geometry, but it does something. I don't know what the hell that is. I'm going to plug into here. I'm going to plug in this into here. Whoops, into here. Because n equals that stuff. So whatever n equals, I'm going to plug that in for it. All right? So I'm going to say it's 30.5 times n. But n is a over 250. And that one function goes straight from a, the square footage I'm painting, to c, the number of dollars I'm spending. Yeah.
You're making up the rules, right? I mean, right? You're not.
What, the c and the n rules? Yeah, I just made that up.
Oh, okay.
Well, the book is making that. I'm looking at the book. But yeah, they just made that up.
Oh,
That might actually be more or less accurate. I don't know.
yeah.
When was the last time you painted a house? You ever, a gallon of paint, does it cover 250 square feet? I don't know. And you go to Home Depot, you get a gallon of paint, is it about 30 bucks? This is close, I guess, I don't know. Whatever. You want fancy paint, what, it's got gold in it or what? Jeez. Some people, they want everything. All right, so what about this? Okay, so let's try that again. So what this does is it just summarizes the whole process of plugging in the 1,000, dividing by 250, getting the 4, multiplying by the 30.5, getting the 122. It's just one step. It's like it's one step, okay? All right, try this again. Let's get used to this idea of plugging the output of one function into the input of another function. That's what composition means. All right, let's practice that up. All right, so the output of this function got plugged into that function, right? Okay. Let's go back to the chirping problem. Remember the chirping problem? Let's say that the temperature in degrees Fahrenheit is a function of the chirp rate, right? Wasn't it? In fact, it was, what the heck was it? A quarter of R plus 40? You're going to get so sick of this graph. This linear function comes up 500 times, okay? But let's say somebody now calculates R as a function of time. What if R, it's found, some biologist has got nothing better to do. It sits up all night with these crickets, and he measures from midnight that R, the chirp rate, is another function of T, the number of hours after midnight. And let's say that is, let's say they figured out it's 20 plus T squared. All right, so at midnight, what is it? T is the number of hours after midnight. So what's T, little t, at midnight? What? Yeah, what's T, but what's T at midnight is what I'm saying. 0, okay? So what's the chirp rate at midnight? If you plug in 0 for little t, 20 chirps per minute, right? Okay? This is what they're saying. So what is it at 1 a.m.? What's the chirp rate at 1 a.m.? 21. What's the chirp rate at 2 a.m.? 24. Do you see what it's saying? What's the chirp rate at 10 a.m.? 120, and so forth, okay? That's what they're saying. So what if I want the chirp rate as a function of time? What if I want big T as a function of little t? Can't I plug in a little t, let's say 0, get 20, plug it back into here, 20 over 4 is 5 plus 40 is 45 degrees? Can I do that all in one step? What is t as a function of little t? Can I do f of g of t? Can you do that? How do you do that?
You replace the R by 20 plus T squared.
Well, exactly. So wherever you see r, you plug in what it equals, 20 plus t squared. So I'm going to get 1/4 of r plus 40, but r happens to be 20 plus t squared. So now you have a function that relates little t directly to big T. So I can plug in the time, the number of hours after midnight, let's say, I don't know, let's say 10, okay? And get straight away, when I work this whole mess out, the temperature at that time, right? So let's do it. 10 squared is 100, plus 20 is 120. 120 over 4? 120 divided by 4? 30. 30 plus 40? So it's 70 degrees Fahrenheit at 10 a.m. Okay? How are we doing? On that particular day, that particular time of the year, whatever, this 20 plus t squared must depend on the season or something, right? It's not going to be the same always. It's not going to be the same every single day, every single weather pattern, every single season, right? This is going to vary over the year. But let's say for today, this works, right? Okay? Questions on composition. That's what we're doing. We're putting one function into another function. That's all we're doing. Okay, we're good? Alrighty. All right, here's a more contrived example. Let's say f of x is 2x plus 1. And let's say that g of x is x squared minus 3. Okay. What does it mean, f of g of 3? What does that mean? That means take the 3 and plug it into who? G. And then take that answer and plug it into F. So plug in 3 here, what do you get? Plug in 3 here. 3 squared? 9 minus 3? 6. So now I have to do F of 6. So take 6 and plug it in where? And here. So 2 times 6? 12 plus 1? 13. That's what F of G of 3 means. But wait, is this the same thing? What's G of F of 3? In other words, is composition commutative? Is it true that the order doesn't matter? Am I going to get the same thing? Sometimes yes, sometimes no. Let's see about now. Plug in 3 where? Into here. So 2 times 3, 6 plus 1, 7. So now I have to plug in 7 into G. So 7 squared, 49 minus 3, 46. So it's not commutative. Not always. Sometimes it is. We'll talk about that. All right. Let's do this out. That was numerically, right? Let's do this a little bit more algebraically. Again, f of x is 2x plus 1. And g of x is, what did I say? X squared minus 3. So algebraically, what does it mean, f of g of x? So I can calculate this for any x, not just 3. That means take g of x itself and plug it into where? Wherever you see x and f, right? So it's 2 times the input plus 1, but the input is x squared minus 3. And what if we want to simplify this? What would you do? So 2x squared minus, wow, why does it do that? 2x squared minus 6 plus the 1 is really 2x squared minus 5. Good. All right, there you go. Well, then, how about this? What's g of f of x as a function in any x I want to plug in? That means take f of x as input and plug it in where? Into, take 2x plus 1 and plug it in where? Into the x squared, right? Okay, so it's the input squared minus 3, but the input is 2x plus 1, right? And then you can simplify that, can't you? How do you do 2x plus 1 squared? Don't say 4x squared plus 1. How do you square a binomial? You got a FOIL? Did you say FOIL? Okay, everyone know this term FOIL? It's your favorite F word, okay? 4 letters, FOIL. All right, so you're going to do 2x plus 1 times itself. Simplify stuff, combine like terms, and then subtract 3, right? All right, I'm running out of room. I'm going to go over here. So g of f of x was 2x plus 1, am I remember? Yes, times itself, and then it was minus 3. Okay. So FOIL, let's see. First times first, 4x squared. Outer times outer, plus 2x. Inner times inner, plus 2x. Last times last, plus 1. And don't forget there's a minus 3. And let's clean it up. Are there any like terms?
2x.
The 2x's combined to 4x. And I hate this. Why is it doing this? Go away. That's a 2. And then what goes here? Minus 2. Perfect. So you see right away that g of f of x is 4x squared plus 4x minus 2 is totally different from f of g, which is simply 2x squared minus 5. It's totally different. Okay, that's why we didn't get the same value for f of g of 3 and g of f of 3, right? Okay. Any questions about composition of functions so far? Are we okay? Have you done this before? Does it sound familiar? And the algebra behind this? A lot of you, well, not a lot of you. Some of you are Nassau students. Did you take Math 109? College algebra? Recently, right? Didn't you do stuff like this in there? Right? Okay. A lot of you all are from high schools, getting ahead in life, I guess. Is this okay? I guess you took Algebra 2 in Trig, Regents, and you got 100 on the Regents, right? Or 98, 96. Really? All right, just checking. And some people are slumming in from other places like Binghamton and SUNY Old Westbury and, yeah. Okay. So since you're from other colleges, you know stuff, I hope. All right, let's talk about inverse functions. Do you know anything about an inverse? What's an inverse function? Not, well, you can sort of like the opposite. Not quite the opposite, yeah. Yeah, blah, blah, blah. All right. Okay, this is what an inverse function is. Now, we use inverse functions a lot in algebra to solve equations, right? Look, let's say I asked you to solve this equation. X squared equals 4. How to get x? Square root. Why? Because if f of x is x squared and g of x is rad x, what's f of g of x? If f of x is x squared and g of x is rad x, what's the composition of f of g? Take g, which is who? Rad x, and plug it into here, right? So you got rad x squared is what? It's x. They cancel. Inverse functions are sort of like opposites, and then they cancel the original function. Inverse functions cancel the original function under composition. And that's what you're doing. I don't know if you realize it, but what did you want to do? Square root both sides? You're using composition. You're square rooting both sides to cancel the square. Right? You're square rooting a square to get rid of the square. That's using inverse functions. That's how you solve equations. Whenever you solve an equation, you are using an inverse function. How about this? What if the sine of x is rad 3 over 2? How do you get x? Well, on the calculator, I don't know who was familiar with the 83 or 84 before we walked in here this semester? You've used it before, right? Isn't there a key in here that cancels sine? Second sign. Do you see the second sign has sine inverse? That's a symbol for inverse function. If I take the inverse sine, the inverse function of sine, of the sine of x, and I do that to both sides, I'll get x, because the sine and the inverse sine functions cancel. That's what inverse functions are for, to solve equations, to cancel stuff. So what do I get here? What's the inverse sine of the sine of x? Just this. This, what?
X.
It's just x, okay. And then do you happen to know the angle whose sine is rad 3 over 2? 60 degrees or pi over 3 radians? So let's say radian, okay? So you can solve equations involving functions by using the composition with the inverse function. That's what inverse functions are for, okay? All right, now, verbally, what does that mean? Well, let's see. Let's say I gave you this function. Let's say P is a population of birds, and T is the number of years since the year 2000. So T right now is the number of years since 2000. T right now is 13, well, 13 point something, I guess, but let's say 13, right? So P is a function of T. P is the number of birds in thousands. So if P is 2, how many birds do I got? P is the number of birds in thousands of birds. So if P is 2, how many birds do I got? 2,000, right? So let's say that f of 13 is 2,000, makes sense. Okay? Okay. Let me ask you this. What does f of 4 mean? How about that? What does f of 4 mean? If you calculate f of 4, what do you get? What does it mean? Plug in 4 in place of which variable? P or T? T, right? So 4 represents what year? 2004, right? So T is the number of years since 2000. So if T is 4, we're in year 2004. What do you get? If you plug in 4, you had the function, worked it out. What does that mean? What's the output of the function? What does P represent? The number of birds. But in this case, the number of birds in 2004. Okay. But that's the easy question. God, you guys just got stuck on the easy question. What does this mean? The inverse function at 4. Huh? No, it's not a reciprocal. It's not a multiplicative inverse necessarily. Though we do, be careful, when you do this to a number, when you see this notation 2 to the negative 1, that does mean the reciprocal of 2 in arithmetic, yes? They're using the same symbol for functional inverse, not multiplicative inverse. It's different. Be careful, that is confusing, I know. But when you attach this to a function, talking about the functional inverse, that's different, yeah.
I was going to say, is it equal to f is -4? Is that what
It's not negative 4. I don't know the number. But whatever number you get, what does it represent? That's what I'm asking. If you actually knew what f of inverse of 4 was, some function, you can plug in 4, work it out, you get a number. What does that number represent? All right, let's put it this way. F of 4 is a population. F inverse at 4 is a time. Huh? What? Okay, that's it. We're done. Go home. I give up. Erase stuff. Erase it. What? Yes. Okay. Okay, this is what I'm saying. That T is F inverse of P. When you're doing the inverse function, when you're doing the regular function, you're plugging into time and you're getting population. But when you invert a function, you're actually physically swapping the domain and the range. So the input is not time and the output is not population. The input is population and the output is time. So what does this really mean? I'm plugging in 4 whats. If I'm plugging in population, remember P was in what units? Thousands of robins or something, right? So this means 4,000 robins. So I'm plugging in 4,000 robins and I'm getting out the year that we had that population, whatever that year was. If such a year exists. It may be undefined, who knows, I don't know. Okay? That's what inverse functions do. They swap the input and the output. They swap the domain and the range. So if your function inputs time and outputs population, your inverse function plugs in or inputs population and outputs time. Okay. All right, let's make this obvious. This is not obvious, right? Okay. You've never heard of an inverse function before?
Yeah.
That's what it means. Okay. You know, I hate to say when people, I'm recording for you too. I'm going to be nice. When other math teachers teach math, why don't they explain stuff? Yes, explain. Right? Do a lot of teachers just like throw it, oh, it is an inverse function, just plug stuff in, you get stuff out, move on, okay, we got to get to the regents, okay? Right?
Yeah.
I don't do that. I explain. You know that reference, do you? You ever watch I Love Lucy? Lucy and Ricky? You know Ricky when he gets pissed off? Hey, Lucy! ¿Qué estás haciendo, Lucy? Right? That's my dad. My dad was just like that. So anyway, Ricky would always say, Lucy, you gotta explain. I don't understand. Explain. Right? You ever watch this? That's how you talk, right? I explain. Okay, let's explain. Let's go back to our favorite function. Every book has a favorite function. I just noticed that. Last semester I was using a different book, and there was this function come up every 5 seconds. So here's my favorite function, apparently. Do you know it? Yes, predict. T equals 1/4 R plus 40. The chirping, right? I don't know why. It just comes up a lot. All right. So this function, T is a function of R, right? T, the temperature, is a function of R, the chirp rate per minute, right? What's the inverse function? This thing is set up so that you plug in R and you plug in the chirp rate and you get the temperature, right? For whatever reason, I want to be able to plug in the temperature and predict the chirp rate. How do you do it? Swap the C and the R, and you're swapping the domain and the range, and you're solving for the R. Yeah, that's how they do it in Regents class, right? Does that sound familiar? Like if it's, okay, this is what they do, ready? I'm going to do it like they do in Regents class. Y equals 1/4 x plus 40. Swap the x and the y. And solve for y. Okay, how do you solve for y, children? I'm pretending I'm in high school, sorry. So solve for y, what do you do? Subtract the 40, so you get, where am I? So you get x minus 40 equals 1/4 y. How do you get rid of the 1/4? So 4 times
Yeah.
x minus 40? Okay. All right, good. Great, that's great. Why do they do that? So that on the same graph paper, with an x-axis and a y-axis, you can graph this, y is a function of x, and this y is a function of x. But notice the x's and the y's swapped. They're not the same. That's really not a good idea. Because when you swap it, the input x is not the input x here. This x and this x means something different. This x was a chirp rate, right? But this x, right, here we're inputting the chirp rate, here we're inputting the temperature. Here we're outputting the temperature, here we're outputting the chirp rate. So I think this is confusing. This x and y are not the same meaning as this x and y. Yeah.
So the relationships change.
So we're swapping the domain and the range.
So the y, which is the t, I believe, turns into the dependent.
Right. The independent is the x. Yeah. It's called independent because you can plug in whatever you want, and then y depends on what you plug in. So y is dependent. There's Greek words for this. So abscissa. Abscissa in Greek means leader, and ordinate, the y's, that means follower in Greek. You don't take Greek anymore? You guys take Greek? When I went to school, when I went to the little red schoolhouse on top of the hill, and I walked both ways in the snow barefoot with my slide rule on my back, we used to take Greek and Latin. No? German, French, Spanish,
Yeah, he's French.
English, hopefully? Sanskrit? Really? Okay. More power to you. All right, fine. But look, this is what I'm going to do. I'm going to just simply solve for R. Solve for R. It's the same process. What was the first step last time? To get R alone, what would you do? Subtract 40. Isn't that the first thing we did last time when it was 1/4 y plus 40 equals x? Okay. So t minus 40 equals 1/4 r. And then what? How do you get r? Multiply by 4. So 4 times t minus 40 is r. So r is the inverse function of t. Okay? It's the same result. But here it's confusing. Here you have to keep track of, okay, this is the chirp rate, but this is not. This is the temperature, but that's the chirp rate. That's confusing. I'd rather label it the way it should be. This is a chirp rate, this is a chirp rate. This is a temperature, this is a temperature. I'm golden. What do you do though to graph it? If you graph it, okay, let's go to the graphs. Now it's easier to deal with this when you're graphing it this way. All right, so let's graph it this way. Go to your calculator and graph this. All right, now let's see what this looks like. So I'm going to clear out. You know what? I'm going to turn off my stat plot. Second stat plot for enter. Okay, and then y equals. Clear that out, and let's type in both of these functions. So if this was f, and this was f inverse, right? So how about 0.25 x plus 40? And 4 times x minus 40. And I don't know, is the zoom 4 okay for this? I like zoom 4 if I can use it. No, because the y-intercept is so huge, plus 40? Yeah. All right, let me zoom out a couple times until I can see stuff. Okay, so zoom out, enter. No, if I enter again, it'll zoom out again. There you go. All right, so that's 1/4 x plus 40, and that's 4 times x minus 40. I'm trying to be very careful here. I want a square window so the slopes look correct. Because look what happens. This always happens. Geometrically or graphically, this is what happens. A function and its inverse are related graphically. How? A function and an inverse algebraically are related by swapping the domain and the range, swapping the x's and the y's, right? But graphically, how is this related to that, do you suppose? Do you see any relationship? This and that?
But it's supposed to be meeting.
They do intersect somewhere. Where do they intersect? All right, good. All right, let's go with that. I'm going to zoom out a little bit more so I can see the point of intersection. Let's see where they intersect, right? Super trace or second trace intersect, and that's close enough. Enter, enter, enter. They intersect at a point such that x and y are equal. That's a hint. What's the geometric relationship between the function and its inverse function? Always. No? All right, let me show you another one. Didn't we just say a minute ago we solved x squared equals 4 by square rooting? Because the square root function is the inverse of the squaring function, right? Take a look at this. Let me graph that instead. I'm going to turn this off for a second, and turn this off for a second. And I'm going to show you what x squared compared to rad x look like. Let's go back to a zoom 4. There's x squared, the parabola. There's rad x. Now, let's make this more obvious. Let me just stay in the first quadrant. Whoops, I messed up. I know, stop it. I didn't mean to put that there. Zoom 4, let's fix that. I want to zero out the mins, the x min and the y min. So x min is 0 and y min is 0 down here. Okay. So let's just look at the first quadrant. How are these two graphs related? And again, where they intersect, what does it look like? What do you think the x value here is? 1 and the y value? 1. What do you think the x value and y value are here? They're the same. That's a hint.
Oh, they have reverse points.
We're reversing the x's and the y's. That's a numerical or algebraic definition. We got that. I want a geometric definition of inverse functions. What's the geometry here? This is called coordinate geometry. No. All right, let's do it again. How about, let's turn these off. And let's compare sine with inverse sine. Right? Those are the inverse functions we did to solve sine x equals rad 3 over 2, right? So second sine. Let me start with a zoom 4. So here's sine. And here's second sine. Let me focus on the part of the graph between negative pi over 2 and pi over 2. I'm going to blow that up. All right, so I'm going to go window. X min is negative pi over 2. And y and x max is positive pi over 2. Just that piece of the graph. I'm going to blow it up. I don't know if you noticed it defaulted to almost negative 2 pi to almost positive 2 pi. All right, I'm blowing it up a little bit. So here's sine, and here's inverse sine. Actually, wait a minute. I meant pi over 4. Sorry, I meant pi over 4. I want to go from here to here. Or just focus from here to here. I think it's pi over 4. Wait. Window, negative pi over 4, and positive. I just want to blow up that one piece because it gets complicated elsewhere. That was the sine, and that's the inverse sine. Why don't they look like they did? They look like lines almost, don't they? What did I do? Any curve sufficiently magnified will look linear. That's not what I want. Right? I messed up the window. I squished it. Well, actually, I stretched it. That's what I did, right? So the slopes are all wrong. So there's a way to fix that. Zoom square. Yeah, but it went back to this, yeah. All right, forget it. Just forget this stuff. Just focus on this piece right here. Is there a relationship between this curve? You know, it's hard to see which is which. Okay. You know what? Go to on the inverse sine, I'm going to make it thick so it stands out. All right, here's sine. And here's inverse sine. All right? It's a relationship between the inverse sine and the sine, just for this piece of the sine right here. You don't see it? You don't see it. Yeah? Y equals x, right. That's why they intersect at y equals x. It's a reflection. Every one of these curves, the function and its inverse is a reflection. The inverse is a reflection of the original function across the line y equals x. So if I graph y equals x, it's a line of reflection. That's why if they intersect, x and y are equal. On the line y equals x and y is always equal. X, it goes to the point 0, 0, 1, 1, 2, 2, 3, 3, 5, 5, right? All right. What if we go back to this one? Turn this off. Turn this off. Turn this back on. Turn this back on. Go back to zoom 4. And for the part, for where the square root function exists, it's not defined for negative x, but for positive x, when you square root a positive number, notice it's a reflection across the line y equals x of the parabola, x squared. If you want to blow it up a little bit, put a 0 here, put a 0 here, maybe make this, the inverse function, thick again. So that's the function, that's the inverse. They're reflecting across the line y equals x. You see it? And I had to be very careful to have a square window to see that the reflection is correct. Otherwise the slopes get all messed up. So geometrically, whenever you look at the inverse function, it's always a reflection across the line y equals x. That's why when they intersect at a point where x and y are equal, because they intersect on the line y equals x. Okay? So go back to the original question, the chirping question. Is that true for these two? Let's put this back on. On here, on here. Now remember, zoom 4 was too small, but then we zoomed out. The y equals x is okay, but the chirping thing doesn't show up. So let's zoom out. Where's the zoom out? 3. That's not enough. Zoom out again. There you go. So there's the original function for the chirp rate. That's the inverse function, and their reflection across the line y equals x. Okay? So an inverse function, how do you get it? You swap the domain and the range. But when you graph that, it's a reflection across the line y equals x. Okay? That's important to note. Here's something else. Are you ready? Go back to this. Didn't we say that arc sine of x is just arc sine, the inverse function of sine of the sine of x is just x, and the square root of x squared is just x. They cancel out. Is that true here? If I do t of r, or f of f inverse, does it cancel out? Does stuff cancel out? Look, this is what I'm saying. Let's see. How do I write this? All right, let's go over here. We said that t is f of r, no, f of r, which is 1/4 of r plus 40. But then we also said that r is f inverse of t, which worked out to be 4 times t of negative 40. So my question to you is, what's f inverse of f of r? Well, let's see what it equals. Let's do it. How do you do f inverse of f of r? Take f of r, which is what? It cancels everything out, is the point. Right. That's the thing is, algebraically we use inverse functions to cancel stuff. This is why. So if we got the right f inverse, this is a way to check that we did it right. Everything should cancel out. So I'm going to take f of r, which is what? 1/4 r plus 40. Plug it in to where? Plug this, this is 1/4 of r plus 40. Plug it into where? Into the t of f inverse. Okay, so that means 4 times the input minus 40, but the input is 1/4 r plus 40. So what happens? Well, how do you simplify this? Please excuse my dear Aunt Sally, parentheses first. Anyone hear that before? Please excuse my dear Aunt Sally?
Yeah.
Right, when you have a whole bunch of arithmetic or algebra to do, resolve what's inside the parentheses first. Now, if you have multiple parentheses, do the innermost first, right? Then do exponents. Please excuse, right? Then do multiplication and division from left to right. Then do addition and subtraction from left to right, like you read a book, right? Unless there's parentheses to change that order. That's called the order of precedence in arithmetic. Right? There's a convention that everyone agrees to do it like this, right? So please excuse my dear Aunt Sally. All right, so according to please excuse my dear Aunt Sally, can I do anything in this inner parentheses, or is everything combined already? All right, so forget the inner parentheses. What about these 40s? They cancel. So all that's left is 4 times 1/4 of r. But what happens to the 4s? And all you get is r. Everything else canceled out. That's the point. That's what you use inverse functions, to simplify stuff. Okay? What about the other way around? What about f of f inverse of t? Does everything cancel out to t? Let's see. All right, let's do that again. So let's write, okay, t is a function of r, is 1/4 r plus 40. R is the inverse function of t, which is 4 times t minus 40. Now we just did f inverse of f of r. What if I do f of f inverse of t, because f inverse of t is, the input is a t, right? So take f inverse of t, which is who? 4 times t minus 40, and plug it into the other function. So it's 1/4 times the input plus 40. But the input is 4 times t minus 40. So what happens to the 4s? What happens to the 4s? They cancel out. So you get t minus 40 plus 40, and what do you get? T. Everything cancels out except for the input variable. It's a way to simplify your equations, is what it is, okay? So now, this is why they do it in Regents class. This is why they do it this way. Let's say that y equals 1/4 x plus 40, and y equals 4 times x minus 40. Let's say this is f, and this is f inverse. But notice the confusion here. X is the temperature here, and x is the chirp rate here. That's confusing. But if you want to figure out f inverse of f of x, how do you do it? You take f of x, which is who? 1/4 x plus 40, and plug it into where? The other function. So 4 times the input minus 40. But the input is f of x, which is 1/4 of x minus the plus 40. That's, where did the 0 go? Okay? So isn't this the same thing? The 40s, what? What happens to the 40s? Cancel. And then, okay, if the 40s are gone, and the 4s cancel, and what do you get? You get x. But what's f? Let's do it the other way. What's f of f inverse? Take f inverse, which is this guy, and plug it into f, which is this guy. So 1/4 the input plus 40, but the input is 4 times x minus 40. So the 4s cancel, they're gone. And the 40s cancel, and you're left with x. So this is how to define inverse functions. Ready? In Regents class. If f of f inverse of x and f of, I said it wrong, and f inverse of f of x both equal x, then you've got the inverse function. So that's the definition of what f inverse is. F inverse is a function such that f of f inverse of x is x, and f inverse of f of x is also x. They cancel out. And that's commutative. That much is commutative. Remember when we composed originally, f of g and g of f were different, but if f is the inverse of g, and you compose them, f of g and g of f work out the same. They both work out to x. All right? That's why they do it that way in the Regents class, so that everything works out to x. But what we're doing in this book, they don't do it that way in this book. So when you read the book, don't get confused. When they do it in this way in this book, they don't end up with x. They end up with the input parameter. Whatever the input is, everything else cancels but it. Which is actually more, it's less confusing, I think. Whatever your input parameter is, r, that's all that's left. Everything else cancels. That's it. Which is the same idea. You just want to reduce stuff, cancel stuff, simplify stuff. That's all you're doing. That's what the inverse function is for. Right? When you're solving equations, right? Does it make any sense? A little modicum of sense. Are we okay with inverse functions and compositions? All right, that's 2.4. I think we killed that to death. All right. Wait, is there another? I'll come back. You know, I'm going to stop the recording early, so I recorded too long yesterday, so I had to render the recording after you guys left, and it took forever. So I'm going to stop the recording like I did the first day. I don't know why I didn't do this yesterday. Stop the recording at a certain point, and then I won't record when I come back and preview the homework. Okay? I'll record on the what's this? Windows Notes, whatever. What the heck was this? Windows Journal, but not on the video. Okay? Because the video takes forever to render. That's what happens when you don't have a desktop screencaster. Anyone do screencasting ever? You're doing it? You know, you guys aren't on YouTube? People screencast for YouTube all the time? No? No? It's more convenient to have a desktop screencasting software because it renders on the fly. As you record, it's rendering the file. So when you're done recording, you're done rendering, you walk away, right? This website renders after you're done recording. So, and it takes a while, so. But it's nice. It gives you MP4s, QuickTime, all that stuff is nice. Anyway, nobody cares. You guys don't like tech talk? You guys aren't techie? Look, it's the 21st century. You guys should know all this stuff. Really? When I started teaching computing, nobody knew anything about what a computer was, right? Now everyone's got a computer in their pocket, for crying out loud. And you still don't know what a computer does. This is sad. Okay, anyway. I teach computing also. If you're wondering what I'm talking about. All right, I think we killed the composition and inverse function stuff. Okay, 2.5, the end of chapter 2, believe it or not. And then, wait, did I do something weird? What am I supposed to be doing today? Where's my schedule? I lost my schedule. There. I'm confusing myself. Okay, today is Wednesday, yes?
Yeah.
Oh yeah, we're supposed to finish chapter 2 and do chapter 3. All right. All right, so let's finish chapter 2 and do chapter 3. All right, chapter 2 is, I'm not going to get too crazy in chapter 2, concavity. All right? This is all you need to know about concavity. Are you ready? Okay. I'm not going to go into a lot of problems and examples in concavity. It's sort of silly. All right. Take a look at the following curves. So pretend this is on an x and y grid, say, right? Here's your function. Let's say this is the origin, okay? Is this function increasing or decreasing? What? Increasing, right? Is this function increasing or decreasing? As you go from left to right, does it get higher and higher? That's increasing, right? What does that mean? The average rate of change, the slope between any 2 points here will be what? If I draw a line through here, what we call the secant line, and we try to find the slope of these two, between these 2 points, what do you know about the slope of these 2 points? It's positive. What do you know about the slope between these 2 points? It's positive. What do you know about the slope between these 2 points? It's negative, right? Okay, so that means this function is what? Decreasing. What about the slope of this line segment here? If I drew a line segment here, what's that slope? Positive or negative? Negative, so the function is decreasing. So if the rate of change is negative, the slope is negative, you're decreasing, right? So are we in agreement that this is an increasing function, this is an increasing function, this is a decreasing function, this is a decreasing function, right? But how are they different? I'm going to say this is concave down, this is concave up, this is concave down, this is concave up. Now how do you know? What? It does, if it holds water, it's concave up? Yeah, a lot of people like to say the parabola like this is a hold water parabola, and a parabola like this is a spill water, right? Spill water, yeah, that's good, yeah. If you're dealing with parabolas, if it's not parabolas, it can get confusing though, right? But, all right, so if this, all right, if you did a parabola like this, would it hold water? No, that's concave down. If you did a parabola like this, would it hold water? That's concave up, okay? But some functions aren't always concave up and always concave down. This parabola is always concave down. This parabola is always concave up. But some functions, they're not always everywhere concave up or concave down. They change. So let me not do it that way. Okay. This is how you know if it's concave up or not. If you take the slope between this point and this point, and this point and this point, and this point and this point, and a whole bunch of points in succession, the slopes are all going to be positive, right? But, all right, let's exaggerate this. The slope from here to here is pretty steep, isn't it? The slope from here to here is not as steep, is it? The slope from here to here is not as steep, is it? This is a positive slope, a positive slope, a positive slope, but it might be a positive 10, a positive 9, a positive 8. If the slopes are decreasing, if they're positive but decreasing, concave down. All right? Now this is also concave down. What's going on here? Let's blow that up. Hello? Where's my pen? Get rid of this. Let's blow this third one up a little bit. If I take successive average rates of change, successive slopes, that's a negative slope, isn't it? From here to here, that's a negative slope, isn't it? From here to here, that's a negative slope, isn't it? But isn't it getting steeper and steeper? In other words, more negative? So if it's a positive slope and getting less positive, or if it's a negative slope and getting more negative, in both cases they're decreasing slopes. That's concave down. Right? If this is 10, 9, 8, they're positive decreasing slopes. If this is negative 1, negative 2, negative 3, they're negative decreasing slopes. So if the slopes are decreasing, you're concave down. All right? If you take successive slopes of secant lines, or the average rate of change from this point to this point, this point to this point, this point, and it keeps on getting lower, it's more and more negative, right? Or getting closer to being negative, right? 10, 9, 8 is going toward the negatives, right? That's concave down. What's concave up then? Well, this slope is positive, this slope is positive, this slope is positive, but the slopes are getting more steep. They're increasing, right? Okay, this slope is negative, this slope is negative, this slope is negative, but it's getting, if this is negative 10, this is negative 1, this is negative 1/2, this is negative 1/4, they're getting more and more positive. They're getting less negative. If the slopes are increasing, they're getting less negative. They're getting more positive. Here, the slope might be 1, the slope might be 2, the slope might be 3, getting bigger and bigger and bigger, right? So if the slopes are increasing, you're concave up. If the slopes are decreasing, you're concave down. All right? That's really all you need to know about 2.5. I don't want to get too crazy with that. I want to get to chapter 3. So are we okay with the definition of concave up, concave down? If the slopes are increasing, you're concave up. What?
So the last one, that one's a negative, or?
These are negative slopes, right? But they're getting less and less negative. This might be like a -2, a -1, a -1/2, a -1/4. They're actually getting bigger. Well, they're increasing. They're getting greater values. They're getting less negative, right? This is getting more positive. This is getting less negative. In both cases, the slopes are increasing, right? Slope of 1, slope of 2, slope of 3, slope of -3, slope of -2, slope of -1. It's still increasing, right? Getting closer to being positive, say, right? All right, so I don't want to get too crazy with that. Let's go to chapter 3. Now we're going to focus on quadratic functions. What's a quadratic function if you graph it? A parabola. Not necessarily a U, but a parabola, right, okay. So that's what we're focusing on here. So kindly consider the following parabola. Really? Thanks. Okay, I don't care. Go away. All right, kindly consider the following function. What if y equals x squared minus x minus 6? All right. That's a parabola because it's not mx plus b anymore. Mx plus b would be if it was missing the square term, right? This would be a line, wouldn't it? Well, wait, I got ahead of myself. Get rid of that. That would be a line, right? The slope is what? -1, and the y-intercept is -6. But that's not what I'm saying. I'm adding this other term here. That adds some curvature. That adds some concavity. That's a parabola, okay? So what if I want to graph it? Well, one way to deal with it is to figure out its intercepts. How do you get x-intercepts? How do you get y-intercepts? Remember this? How do you get a y-intercept? On the y-axis, what do you know about every point on the y-axis? Every single point on the y-axis, x equals 0. So if I plug in 0 for x, I'm going to get the y-intercept, right? All right, so what happens if I plug in 0? What are you doing? Give me a pen. So now it's acting stupid again. Okay, plug in 0, square it, minus 0, minus 6, you get -6, right? Okay, so that means that when you plug in 0, you get -6. This point is the y-intercept of the parabola. How do you get the x-intercept? What do you know about every point on the x-axis? Every point on the y-axis, x equals 0. But every point on the x-axis, y equals 0. So what if I plug in y as 0 and solve for x? How do you solve a quadratic equation? That's what we're talking about. How do you solve a quadratic equation? Can you solve that? You set it equal to 0 in standard form, and you factor, and you set the factors equal to 0, right? Because the fundamental theorem of arithmetic says that if two numbers multiply out to 0, one or both of them have to be 0, right? What? Okay. So can you factor that thing? How do you factor that? You're looking for two numbers that multiply to -6 but add up to -1. All right, so let's try that. If it's not factorable, you could always use the quadratic formula. We'll talk about that too. All right, but I think this one's factorable. What multiplies to -6? Now, be careful what we mean by factorable, okay? We're talking about integer-wise factorable. Can you come up with, in your head, two nice easy integers that multiply out to -6 and add to -1? Now, some people can factor non-integer-wise, because this may be factorable with radicals. This may be factorable with i's. What's I? The square root of -1, right? And most people do that by using the quadratic formula. But you don't, if you get used to doing this a lot, you can actually factor with any kind of number. But when I say, is this factorable, I mean integer-wise factorable. Can you find two nice easy integers that multiply out to -6 and add to -1, and you say, -3 and +2? Okay. So in other words, x plus 2 and x minus 3 would FOIL out, if you want to check this, would FOIL out to that, wouldn't it? Right, so 2 times -3 is -6, 2 plus -3 is -1, perfect. If you FOIL it out, that's what you're doing, right? Because you FOIL x times x gives you the x squared, then the outer would be negative 3x, the inner would be positive 2x. You're adding them to get the negative 1x, and then the last times last is negative 3 times 2 is negative 6, right? So yeah, this works. So now what? So if this times this equals 0, you know that this had to be 0 or this had to be 0. So say so. So I'm going to say it over here. X plus 2 has to be 0, or x minus 3 has to be 0. So solve for x, and you get x is negative 2 or positive 3, and you can always plug it back in to check. All right, so now I know a lot of stuff about this parabola. I know 3 points already. I know the point 0, negative 6, and I know the point negative 2, 0, and positive 3, 0. So let's graph it. I'm ready to graph it. No Ziggy involved. Right? We'll check it with Ziggy in a second. All right, so I have a parabola that goes through these 2 points. Negative 6 on the y-axis, negative 2 on the x-axis, positive 3 on the x-axis. Let's do that. All right, so negative 2 on the x-axis. That's a point, x-intercept, right? Positive 3. And the y-intercept was negative 6. 1, 2, 3, 4, 5, 6. Negative 6. All right, so I know that. So is that enough to graph the parabola? Not really. I really need to know the turning point, right? If it's a hold water parabola, the minimum point, that's a turning point, or the maximum point if it's a spill water parabola, the top, that's a turning point. I need the symmetry to make sure I got the complete graph, right? Do you know how to get the axis of symmetry of a parabola? Let me remind you that you know the quadratic formula, right? Let me go one page further. If you're solving ax squared plus, I hate that, ax squared plus bx plus c, where a, b, and c are any real number you like. What's x? Negative b, I'm trying to solve the equation, quadratic formula. Wait, plus or minus the square root of b squared minus 4ac all over 2a, right? Now, what this really means is the x-intercepts are negative b over 2a plus or minus the square root of the discriminant over 2a. What does that mean? This is the axis of symmetry. This is how far the x-intercept is from it. So if the axis of I'm going to make up something. Say the axis of symmetry is at x equals 2. Now remember, x equals 2 is what kind of a line? Horizontal, vertical, or slant? Vertical, right? Plus or minus, I don't know, 1. That's what the quadratic formula is giving you. It's giving you the x-intercepts as a function of the axis of symmetry. If the axis of symmetry is 2, one x-intercept is 1 to the right, 3, and 1 to the left, 1. Okay? So this part, negative b over 2a, that's the axis of symmetry. Let's go back. So if I'm graphing y equals, what was it, x squared minus x minus 6, right? What is negative b over 2a? What's the b in that equation?
1.
Negative 1, right? So negative 1 is 1 over 2a, but a is the number in front of the x squared term. What is it? 1. A is 1, b is negative 1, c is negative 6, right? So if I plug in 1 here and I plug in negative 1 here, I get 1/2. So the axis of symmetry is right here at x equals 1/2. So how do I get the turning point? How do I know how far that parabola goes? By the way, since A is positive, is this a hold water or a spill water? It's a hold water. So I'm thinking that it's going down to a minimum. How do you find the min? That's the question. How though? What are you going to do? You're going to plug in what? Into what? You don't need a calculator for this. You're going to take the 1/2, the x value here, and figure out the y value here. I want to know that point, right? So take the 1/2 and do what with it?
Oh, plug it.
Plug it into here. Okay, so y is going to be 1/2 squared minus 1/2 minus 6. Okay, what's 1/2 squared?
1/4.
1/4. What's 1/4 minus 1/2?
1/2.
Whoa.
What's it?
It's negative 1/2, isn't it? Because if you need common denominators, you multiply top and bottom here by 2, right? So you get 2/4. So it's 1/4 minus 2/4. 1/4 minus 2/4? Negative 1/4. So I get that y of 1/2 is negative 1/4 minus 6. In other words, negative 6 1/4. Negative 6.25, right? So I have all these points. I have this point, negative 2, 0, 3, 0, 0, negative 6, and this point right here, which is 1/2, comma, negative 6 1/4. So there's my parabola. Just join these dots. But now you know the symmetry and the turning point. And my pen sucks, but there you go. Okay?
Did that help you find out?
Well, this is, again, when I used to go to the Little Red Schoolhouse on top of the hill, both ways, in the snow, barefoot, with my slide rule. We had bear skins and stone knives. We didn't have a graphing calculator. That's how you graph. You find the intercepts, the x-intercepts, the y-intercepts. You find the mins and the maxes. You find the concavity. You find where it's increasing, decreasing. We did all of that. Isn't it clear in this graph where the function's increasing or decreasing? Where is it decreasing? Where the y value is decreasing? As you go from x, as you go x from left to right, where the y value is decreasing? Right here, right? In other words, when x is less than 1/2. Where is the function increasing? When x is greater than 1/2. Do you see all the intercepts? The x-intercepts, the y-intercepts. Do you see all the mins and the maxes? There's only a min. Do you see all the concavity? It's only concave up. That's a complete graph. That's what you want to see on your graphing calculator if you want to get a complete window on your graphing calculator. Look, if you put this on your graphing calculator, look what you get. Go to y equals, clear out all this junk. This is chapter 2 junk. Okay. And let's just graph this thing. What was it? It was x squared minus x minus 6, right? And if you just pick an arbitrary window like a zoom 4, you may not see all of that, right? That's not a complete graph. It's a square window. The slopes are all right. The curvature is all right. Circles look like circles. Slope of 1 looks like the slope of 1. Concave up, concave down, increasing, decreasing. That's there. But you don't have all the intercepts. You don't have all the mins and the maxes. You don't know where it's increasing, decreasing. You don't know it's always concave up. So you'd have to change this a little bit. How about a zoom out? Because zoom out, what's nice about zoom out is it preserves the square window. And there's a complete graph. But isn't that what we graphed? That looks like negative 2, 0 to me. That looks like 3, 0 to me. That looks like 0, negative 6 to me, or maybe not. Trace it. There it is, 0, negative 6. How about, can we trace the positive 3 for x? No, I can't. Not in this window. Okay, go back to zoom 4. Can I trace the positive 3 for x? Make sure that that's where that y equals 0. Positive 3 for x, y is 0. Well, how about negative 2 for x? Is that when y is 0? Negative 2 for x. Is that when y is 0? Yep. If I do second trace value at 0, is that when y is negative 6? Yep. What if I do zoom out and I want to figure out that minimum point? Do you know how to make the calculator do that for you? Super trace, second trace, what? Min, which is 3. And then, now the min is over here, so pick a left bound to the left of the min, enter, pick a right bound after the min, enter, then you don't have to guess, enter. And was our min correct? We said the min was going to occur at x equals 1/2 and y equals negative 6.25. Is that what it says? Within round-off error. There's round-off error, the calculator lies. It should be 0.5 exactly, right? Why is there round off error on the calculator so much? Why do we round off to 3 places when we get wacky decimals? Or round it off to something to get rid of that round off error? Because it's a computer. And at the base of the computer, all the arithmetic is done in binary. And guess what our next YouTube is? YouTube Wednesday. It's all about that. Why computers round off wrong. Why there's round off error on computers. Because we're entering the problem in base 10. But the computer does everything very quickly, very efficiently, very accurately, actually, in base 2, binary. And then it has to convert all that back to base 10. The converting to base 2 and back to base 10, there's going to be round off error in there. Because some numbers that can be represented exactly in base 10 cannot be represented exactly in base 2 and vice versa. So sometimes you get crazy round off error. Sometimes a number that's rational terminating in base 10 is rational non-terminating in base 2. Right? Remember, rational numbers are either repeating or terminating, right? But sometimes in different bases they act differently. So when you convert, you lose digits and there's round off error. So that 0.500107, that's a lie, it's 0.5. And the min is negative 6.25, like we said. Didn't we say that? Negative 6 1/4, we said that, right? Okay. All right, so now what? What if you can't do it that way? All right. What if I perturb this a little bit? Let's make it, let's say all right, let's say I want to solve this equation. X squared minus x minus 5. What did I just do? Instead of minus 6. I took the graph and I shifted it up 1. So the roots are different. So, and then, right? So then you said something else? You said it may not be it's not factorable, is it? And again, integer-wise factorable. It doesn't mean it's not factorable, really. Because people can't factor these with radicals or i's in their heads without even using quadratic formula. How do you solve for the x-intercepts? When y is 0, what's x? What we call the zeros of the function. You can't factor it, so what's your fallback position? Can you think of 2 nice easy integers in your head that multiply out to -5 and add up to -1? No. So you say the quadratic formula, right? Okay. So that means x equals, let's do it. All right, give me numbers. Do you know the formula? I need negative b, so what's that? Not -1. Negative b is 1, because b is negative, right? So the opposite of b is 1, plus or minus that same b squared. b is -1, so square it. What do you get? 1. Minus 4 times a times c. Who's a? The coefficient here. 1. Who's c? The coefficient here. -5. All over 2 times a, but a is simply 1, so 2 times 1 is just 2 anyway. So you get 1 plus or minus. What's a negative times a negative? Positive. So this is 1 plus what? 20, so rad 21 all over 2. That's some god-awful number. That's a beast. What is that? I don't know what the heck that is. Look, go on your calculator. If I say supertrace, wait, let me go back to Zoom 4. This is the one with the -6. It was factorable, right? If I do supertrace 0, say over here, on the right, where am I? There. So give me a left bound a little bit below, give me a right bound a little bit above. It's going to give me an exact answer of 3, right? But perturb it a little bit. Make this 5. Now the roots are different. It's not hitting 3. It's not hitting -2. You're hitting something less than 3. So how do you get that? Well, supertrace 0, left bound, let's say a little bit before there, around here somewhere. Right bound, so finds the sign change somewhere in between. These y's are negative, these y's are positive. It's trying to figure out where the sign changes. And now you get 2.71791, god-awful mess, irrational number. Why? I'm saying that's an irrational number. Never ends, never repeats. How do I know that? How do I know that's irrational? How do I know that's not some kind of fractional weird number? Because it could be. Because I got the answer sitting right here. That 2.791 is what? There's two answers here. Do you see there are two answers here? 1 plus rad 21 over 2 and 1 minus rad 21 over 2. Which one of these is 2.791? 1 plus rad 21 over 2, right? And then this one would be the 1 minus rad 21 over 2, right? So let's check that out. Let's see. What is quantity? 1 plus rad 21 all over 2. The 2.791 thing, right? A little bit less than 3. The other one is a little bit to the right of negative 2. Let's see. Second enter. Change this to minus. And it's a little bit to the right of negative 2. There it is. Negative 1.791 something. Those are irrational results. You're not going to get that from factoring. You can't. Not integer-wise factoring, right? All righty. Okay, that's good. That's good. We did that. We did that. We'll get to that in the homework. Okay, that's section 3.1 done. A little basics about parabolas: x-intercepts, y-intercepts, factorable, non-factorable, concavity, mins and maxes, increasing, decreasing, that stuff, right? That's basic stuff. All right, here's 3.2, and that's all there is to chapter 3. Chapter 3 is 2 sections? Wow. Okay, here's 3.2. Kindly consider this parabola. Y equals x plus 3 squared minus 4. This is also a parabola, because if we FOIL it out and you combine the like terms, you're going to get ax squared plus bx plus c stuff, aren't you? Let's see if that's true. Let's see. Let me go here. Y equals, how do you square x plus 3? FOIL it. Don't write x squared plus 9. I know people want to write that. Don't write x squared plus 9. When you FOIL a binomial, when you square a binomial, you're going to get a trinomial. Okay? X plus 3 times x plus 3 minus 4. So what do you get? Do the FOIL. First times first, x squared. Outer times outer, 3x. Inner times inner, 3x. Last times last, 9. And don't forget the minus 4. So the x's combined to how much? 6x. And the constants? Plus 5. So this is still of the form ax squared plus bx plus c. It's still parabolic. It's still quadratic. But this is known as standard form, a standard form parabola, because just looking at it, you can graph it in 2 seconds. Ready? If you FOIL this out, you know it's going to be a hold water, right? You know that it's not going to have a negative x squared term, right? If when a is negative, it's spill water. When a is positive, it's hold water, right? I know that. 2. I also know that the turning point is at negative 3, 4. Sorry, negative 3, negative 4. What? If you write your parabola in standard form, this gives you the turning point. All right? This is of the form y equals x minus h plus k, where the point hk is the turning point of the parabola. And the turning point of the parabola is significant when you want to maximize a quantity or minimize a quantity, because the turning point is the min or the max. If it's spill water, it's a max, the turning point. If it's a hold water, it's a min, the turning point, right? And we do a lot of that stuff with economics, minimizing expenses, maximizing profits, that kind of stuff. That's going to come up a lot in the word problems. Hang on to your hats, okay? So what's h? If x plus 3 is x minus h, what's h? Negative 3, because x minus negative 3 is positive. And if I'm adding k, what's k? Negative 4. So in this example, negative 3, negative 4 is a turning point. So I got the min, and I know that it's concave up. That much I know. To get the other intercepts, I'd have to play around with it some more. But look, graph it on the calculator, see if that's what's happening. Let's graph exactly this on the calculator. Whoops, not that. That. Not that. That. Okay. So y equals, clear that. Okay. So I'm going to graph this. It's going to be quantity x plus 3 squared minus 4. How about a zoom 4? I like zoom 4. Well, is it possible that the turning point is at negative 3, negative 4? I think so. All right, it's not going to be a square window. Let's make the y min a little lower. How about -5? This will mess up the squareness. But look at it. The turning point is at -3, -4, isn't it? Let's make sure. Super trace, min, left bound. Let's find a little bit to the left of what we think it is, -3, -4. Zoom, over there. Right bound, a little bit to the right of what we think it is. Zoom, so you don't have to guess, just hit enter. And you get the min is at -3, -4. Again, round off error. Wacky decimals, round off to 3 places. Usually get rid of the round off error on the calculator. Okay? All right, and it's concave up. It's increasing concave. Well, it's not increasing, but it's concave up everywhere, right? Okay, so it's sort of nice to be able to convert general form parabolas to standard form parabolas. Let's see if we can do that. How do we get, look, it's easy to take from here, to get from here by foiling out to here, right? Isn't that all we did? We foiled it out, combined like terms, cleaned it up a little bit. That's easy. How do you go backwards? How do you get this to look like that? So it's easy to graph, yeah.
You just put square in the first formula, that's supposed to be a square.
Wait, what'd I do? Wait, this is a y here.
No, the very first one.
Y. Where? Square here.
Up top.
Oh, square here. Yeah. I'm sorry. You're right. Ding. Yes, I'm trying to match this with this. Yeah. Okay. So it's easy to go from here to here. You're foiled, right? But how do you go backwards if you want to? What if you're given this and you want to make it easy to graph? Let's see. Let's find out. Let's take this exact question and see if I can reverse the process, okay? So what is it? X squared plus 6x plus 5. Okay. All right. So you do what's called completing the square. You ever complete the square? Okay. So y equals x squared, what the heck was it? Plus 6x plus 5? Okay. Okay, plus 6x plus 5. Now the thing is this, I want to make it look like this. Something squared plus 5. I want to figure out something that when you factor it, you get the same factors twice. Because when you FOIL this out, you multiply the factor by itself, like x plus 3 times x plus 3. Can I make this behave that way? This isn't factorable, as is, right? Can you? Well, actually it is. What multiplies to 5 and adds to 6? 1 and 5, right? This is factorable, but I don't want it. I don't want to factor it such that it's x plus 1, x plus 5. I want to factor it such that it's x plus something and x plus the same thing, so that it's a square. So it's a perfect square. It's something squared. So this is what you do. You complete the square. You say, look, the 5 is messing me up. Put it over here somewhere. Okay? What I want to do is figure out a coefficient that gives me a perfect square trinomial, which means that when you factor it, both factors are the same, like x plus 2, right? So I can write it as x plus 2 squared or something, right? So this is the game plan. This is the process. This is the pattern. Whenever you have something that foils out the same way, something that foils out with x plus 2, they're the same way, right? This is what happens. You get half of this coefficient here. What's half of 6? 3. Okay. But now if you FOIL this out, do you get that? What I want to do is I want to replace this with this. Can I? Are they the same? The plus 5 is still out here, right? But is this the same as this? No. Because this factor says x times x plus 6, not as x plus 3 times x plus 3. If I FOIL this out, what do I get? X squared plus 6x plus 9. Oh, okay. So, So I have to, I'm going to say, all right, this is the same as this plus 9. This is the same as this plus 9, but now I've changed the problem. So I got to fix it. Minus 9. What happens when you add 9 and subtract 9? You're adding 0, that's nothing. But what's 5 minus 9? Negative 4. So this turns into negative 4. So if you graph this, doesn't it go through negative 3, negative 4? Doesn't it go through negative 3, negative 4? Isn't that what we started with? Okay, so completing the square is reversing the process. Okay? That's called completing the square. Okay, here we go. Right? I said if we start with x plus 3 squared minus 4 and we FOIL it out, you end up with x squared plus 6x plus 5. But reversing the process, using this thing called completing the square, I started with x squared plus 6x plus 4, and I ended up with x plus 3 quantity squared minus 4, what I started with. This works. Okay. So it's easy to graph, right? All right, what about this one? What if I want, let's see if I can find a good one. All right, let's try a new one, a different one. Let's say, okay, is this good? Yeah, that one, okay. All right, here's another one. How about this? Let's complete the square on this one. What if y equals, again, ax squared plus bx plus c form, general form, right? So like negative 4x squared minus 12x minus 8. Can you make this look like x minus h squared plus k? That's what I want. Can you make it look like that? It doesn't look like that right now, right? How do you do that? Well, huh? Move the 8? Well, yeah, I put the 8, I get the 8 out of the way. All right, look, let me get rid of this. Go away. Go away, go away, go away, go away. Go away, go away, okay. All right, so let's do it. Here we go. Get the 8 out of the way. Just get it over here. What I want to do is I want to come up with something squared equals that, right? But the first time I did this, was there a number in front of the x squared? No, there wasn't. You know what? Let's make it easy. Can you factor out that negative 4?
Yeah, that's what I was gonna say. Can't you just take out?
Just take that, get that out of the way. Make it easy. So, because the way we figured out how to complete the square, it was always 1x squared to start. You could always make it that. So let's do that. So take out the negative 4. What's left? Just factor out a greatest common factor. What's left now?
X squared,
X squared minus 3x minus 2. Okay, now let's do what we did. The negative 4 is just hanging out here. Just focus on what's in the parentheses. Okay? So what did we do last time? What did we square? We took the middle coefficient and we
X,
chopped it in half. So that would be negative 1.5 and negative 3 halves. Okay, I'm going to write it that way. X minus 3 halves. But now if we FOIL this out, you're going to end up with negative 3 halves squared. What's negative 3 halves squared? Look, FOIL it out. Look, x minus 3 halves times x minus 3 halves is not x squared minus 3x. What is it?
If you took out the negative 4, wouldn't it turn into a positive?
Oh yeah, I'm sorry, I didn't change the signs. Yeah, this is positive. This is everybody's positive. Sorry, you're right. Everybody's positive. Right. But this is I don't know if you caught this part of the pattern. If you actually square this thing, you don't get this. You get this plus this squared, don't you? Because look, do it. First times first is x squared. Outer times outer is 3 halves of x. That's a 3. Okay, inner times inner is also 3 halves of x. That's a 3. I hate that. And then last times last is 3 halves times 3 halves, 3 halves squared. 3 times 3 is 9. 2 times 2 is 4. So you get, what's 3 halves of x plus 3 halves of x? It's 3x, right? 3 halves of 3 halves is 3. All right, so you get x squared plus 3x plus 9 fourths. Yuck. So I can't replace this with this. I have to replace this with this, which means I added 9 fourths to the problem. How do I fix that? I added 9 fourths to the problem. It's not part of the problem. How do I fix it? Here you're going to fix it by subtracting it away. So what's 2 minus 9 fourths? Negative a fourth, right? Because that's 2 over 1. How do you get common denominators? Multiply top and bottom by 4. So it's 8 fourths minus 9 fourths is negative 1 fourth. Okay. So is it in the form that we want? Let's see. This is what we got. We got y equals negative 4 times the quantity x plus 3/2 squared minus 1/4, wasn't it? Is that what we wanted? I wanted y equals x minus h squared plus k. So am I in the right format? Not quite. All right, what if I distribute that negative 4 back in? Remember, we took it out? Let's put it back in. All right, now I get negative 4 times x plus 3/2 squared. But what's negative 4 times negative 1/4? Positive 1. Positive 1, isn't it? Because 1/4 of a 4 is a 1, and a negative times a negative is a positive. So what's k? It's 1. And what's h? Careful. What do you subtract to get positive 3/2? Negative 3/2. So the turning point is negative 3/2 for x, positive 1 for y. And this negative 4 is a dilating factor. It makes it steeper, it makes it more steep parabola or less steep parabola. It's just a dilating factor. It has to do with it changes the directrix. Have you heard of this word, directrix? No? Have you heard of locus? The locus of all points equidistant to a point is a circle of a certain radius, right? The locus of all points equidistant to a line is 2 lines equidistant to that line on either side, right? You've heard of locus? What's a parabola? The parabola is the locus of all points equidistant to a line and a point. The line is called the directrix, the point is called the focus, and the parabola is stuck in between, right? That negative 4 affects how far the directrix is from the turning point. I don't want to get that crazy, because then I have to start talking about lattice rectum. And that's just not nice. What? You guys don't know nothing about geometry? Did you take geometry? Did you take geometry? Did you ever do locus? No. Oh, God. Okay, children, what's a parabola? A parabola is a locus of all points equidistant to a line and a point. Between this point and this line, between this line and this point here is right, it's smack dab in the middle, right? But between this point and this line, this point is halfway, and this point is halfway, and this point is halfway, because we're measuring the distance of the line to the curve perpendicularly. All right, so if you try to measure the distance from this point to this point and this point to this line, that's the point that's equidistant to the point in the line. If you want to measure the distance between this point and this point and this point and this line, that's the point that's equidistant to the point and the line. And you get a parabola. Pretend it's a parabola. Right? This is called the directrix. This is called the focus. This is called the turning point. This is called the lattice rectum. This line segment over here. Usually when you graph a parabola, all you need is the turning point and the endpoints of the lattice rectum. That's another way to graph the line. That number in front of the x minus h squared plus k, that negative 4 in front, that affects this distance. I don't want to get crazy with that. You can use the calculator to graph stuff like that, okay? All right? But this is important. Have you ever heard of a parabolic mirror? Have you ever heard of a parabolic microphone? Have you ever looked at the headlamp of your car? Right? Have you looked at the lamp of the car? The cross section is a parabola. It's a paraboloid. It's a parabola of revolution. Why? No? Nobody knows what a parabola is good for? You guys, are you kidding me? You know. Okay. This is called the focus for a reason. Because if you have, let's say you have, anyone have satellite TV? Dish TV or whatever, right? You have a geosynchronous satellite out in space, right? It means it's following it's following the rotation of the Earth. So if it's above you today at this location in the sky, it's still there tomorrow, it's still there the next day. It's always in the same place relative to you in the sky from the Earth, right? That's geosynchronous? Okay. You're getting transmissions from the satellite. But as those transmissions come down, they radiate. They get what do you call it? Less dense. I don't know. They dissipate. They dissipate, right? And they get wide, and it's omnidirectional. What you want to do is take those signals that are coming from space and bounce it off a mirror, well, an antenna that focuses that signal to the same point all the time. No matter where that transmission ray is coming in from, it gets bounced off of the parabolic satellite dish and focus the data to the same receiving point. That's the focus. So that no matter where that transmission is coming from, it gets focused and you get a good signal. Right. Now think of that backwards. Think of this as a mirror, and this is a light bulb, and this is the headlamp in your car. And the light from the light bulb goes in all different directions, right? But when it hits the parabolic mirror, it gets focused in this direction so that all the rays come out in parallel form, and they all get concentrated in a certain direction, and that's how your high beams work on your car. You ever put the high beams on at night, right? That's why you don't get crashing in the middle of the night, because of parabolas. See? Locus matters. You know, you didn't know about that. What?
No, I love Verizon.
Now you love locus. What?
High beams, it's paraboling or whatever, but then
Well, the low beam and the high beam are it's still parabolic, but you're focusing it up instead of focusing it toward the ground, so you don't blind people in front of you. You know, right? Do you always drive around with high beams on? I hate people like that. Okay. Anyway, so all right. Now look at this. Kindly consider the following. What if I want to solve this equation? Ax squared plus bx plus c equals 0. For any a, b, and c, a real number, and I don't know the quadratic formula. Don't know it. Sorry. Whoops, forgot. Can you derive it now from scratch? You can. Look, this is what you do. What did we do? I'm doing the exact same steps I just did 5 seconds ago. Remember that -4, we factored it out? That's the a. Factor it out. How do you factor out that a? You know, I don't want to do it that way. Let me make it easier. I'm going to make it easier. Hang on. Can I get this c out of my face? How do I get rid of this? Subtract it. Okay, let's get that out of the way. All right, let's just do that. Okay. I'm not doing anything illegal algebraically, right? You're allowed to subtract c from both sides? Okay. So now it's negative, right? Whatever it was, now it's the opposite. Okay. Now factor out the a. So it's easy to complete the square. I'm trying to complete the square. So what do you get if you factor out a? Now remember, factoring, greatest common factoring is just like dividing, right? So a into a is 1x squared. So what do you write here? Plus b over a x. Okay. You see what I'm doing? I'm trying to complete the square. If I can complete the square, if on one side I have a perfect square, I can solve it by square rooting, right? Haven't we seen that? So I'm going to try to make the left-hand side a perfect square, square root both sides, solve for x, make it easy. That's the game. Okay? But to do that, I'm going to use completing the square. Okay. Now, how do you complete the square? You say a times something squared equals -c. So what's the something squared? You know, this a is bothering me. Can I get rid of the a also? What if I divided both sides by a? Can I do that? After factoring it. All right, I'm not skipping steps. All right, now you can't make me. I'm not going to do that. Let me not skip steps. Go away. Go away. I'm trying to make it easy, sorry. There's an easy way and a hard way to do this. Erase. Why isn't it erasing? Oh, there it goes, okay. Can I just divide both sides by a, get that out of my hair? Right, okay, so x squared plus b over ax equals negative c over a. Okay? But I'm trying to make it simple. Believe it or not, let's make it easy. All right, now let's complete the square. Let's make this a perfect square, so it's easy to solve for x by square rooting. All right? Now this stupid pen app, I'm out of paper already. All right, so I'm going to start over on the next page. What is it? X squared plus b over ax? All right, let's go here. X squared plus b over ax equals negative c over a. All righty, except this is an a, and this is a square. You know, I hate this pen. Ugh. X squared. Okay, good. All right, now, use completing the square. How do I make this a perfect square? This side. You take this term and you, what did we always do? Divide it by 2. So it's x plus b over 2a, half of b over a. Right? But remember, if I replace this with this, that's wrong. Because if I FOIL this out, I don't get that. If I FOIL this out, I get that plus, wait, I wrote that wrong. There's no x here. If I FOIL this out, I get x squared. I get bx over 2a plus bx over 2a is bx over a. But then I also get, last times last, b over a 2a times b over 2a. What is that? What's b over a times b over 2a? What's b over 2a all squared? No, you don't see it? Look. If I back this up. When I completed the square here, wait, not here. When I completed the square here, what I ended up doing was I squared the 3 halves. 3 halves times 3 halves ended up being an extra 9/4 that I had to get rid of, right? Okay. Over here, the same thing. 3 squared added the 3 added a 3 squared that I had to get rid of, right? In other words, this doesn't replace this. This replaces all of this, right? It changed the problem. All right, so the same thing's happening down here. I have to square this to replace it. This does not equal this. This equals this plus what? Square this. What do you write? B squared over 4a squared, right? But wait, if this doesn't replace this, it replaces all of this, I change the problem by adding b squared over 4a squared here, so I better add it to both sides to fix it. Okay? You see what I did? Replacing this with this, added this to the left side, so I'm going to add it to both sides, instead of subtracting it from here. Okay. What does that do for you? How do you add 2 fractions? How do you add 2 fractions? That's what this is. You need a common denominator. All right, so what would you multiply top and bottom here by? 4a? Okay, so multiply top of this by 4a, top and bottom of this by 4a. You get 4a squared on the bottom. What do you get on the top? Negative 4ac. So let me write that. b squared minus 4ac all over 4a, that's an a, and that's a 4a squared. Does this sound familiar at all? Is anything looking familiar here? That b squared minus 4ac thing, that should look familiar, right? That's what I'm going to get. All right, so how do you solve for x? Well, can you get rid of the square? Square root both sides, right? Okay. So x plus b over 2a equals the square root of the numerator, which is not a perfect square, over the square root of a denominator, which I can actually square root. Right? The square root of 4 is 2, the square root of a squared is a. So I can actually square root that piece, so I can't square root the other one, so leave it. Now be careful. What's the square root of 4? 2? No. What's the square root of 9? 3 or negative 3. Oh, don't forget, plus or minus. A positive root and a negative root, right? All right, one more step to get x alone. What do you do? How do you get rid of this? Subtract. So x equals negative b over 2a plus or minus the square root of b squared minus 4ac all over 2a. Does that look familiar? That's the quadratic formula, isn't it? We just derived the quadratic formula from scratch. So what's the quadratic formula really? It's solving quadratic equations using completing the square for you. When you plug in a, b, and c into the quadratic formula, it's doing all the completing the square stuff for you. So you've just solved every single quadratic equation there is for every single one of its roots. Aren't you amazing? All right, and by the way, how do you add or subtract two fractions with the same denominator? You already have a common denominator, so just add the numerator. So negative, so this is, in fact, negative b plus or minus the square root of b squared minus 4ac all over the common denominator, 2a. Same thing. Ta-da! That's a ta-da. That's a aha moment. That's a ta-da moment. That's big stuff. You know, people used to pay money for this. In the 1700s, in Paris, well, all over France, they had mathematical competitions. People would come up with new ways of solving equations that other people wouldn't know how to do and pose the problem to other people, and whoever could solve the problem would win the money. It would be a bet. This was hidden for years, centuries. Nobody would tell anybody else about this because they made money knowing this. This was top secret stuff. This is big stuff. Whenever they learned how to solve a new equation, they made more money. They kept it secret. It wasn't like open source software like they have today. Everybody shares everything. Social media, everybody talks about, their bowel movements online every 5 minutes, right? It wasn't like that. Yeah. Question?
Yeah, what are the pages that we can study?
For the test on Monday is chapter 1, 2, and 3. The test on Monday is all about chapters 1, 2, and 3. So the homework pages from chapters 1, 2, and 3 are good practice. Okay? All right, let me just render this thing. Pause.